Welcome to Math TV with Professor V. In this video, we're going to look at solving 4 different problems that have to do with related rates for Calculus 1. If you haven't watched my introductory lecture on related rates, I'll link it here, but otherwise I'm just going to jump right in and work out these problems for you guys. So first one, water is falling on a surface, wetting a circular area that is expanding at a rate of 7 millimeters squared per second. How fast is the radius of the wetted area expanding when the radius is 152 millimeters? So what you want to do right away is go through the problem, list out all the information that they've given you using appropriate notation. So here we can see it says the area is expanding at a rate of 7 millimeters squared per second. So that means the rate of change of the area, or dA dt, with respect to time is equal to 7 millimeters squared per second. All of your derivatives when you're working on related rates problems will be with respect to time. That's what a rate is, how something is changing with respect to time. Okay, what do they want from us? They want to know how fast is the radius expanding. So what they want is the rate of change of the radius. So they want dr dt when the radius, when r is 152 millimeters. When they give you that one specific piece of info that relates to the moment of time that they're interested in, you save that for the end. Okay, so the 152 millimeters, we're saving that for the end. I want dr dt, and they gave me dA dt. So here's where your brain needs to go. You're going to look at the two variables in play, namely area and radius. And in particular, we're dealing with a circular region. So can you think of a formula that relates the area and radius of a circle? Don't worry about any derivatives just yet. Sure, we know one, right? So we know the area of a circle is equal to pi r squared. And the only variables in this equation are a and r, so that's great. Once you've identified how the variables in play are related, you take that equation and you always differentiate with respect to time. This is a related rates problem, yes? Okay, good. Let me spread it out so you can see what we're going to do so nicely. I'm going to take the derivative of both sides with respect to time. And notice there's no t's in this equation. So I'm doing implicit differentiation, yes? Wonderful. Derivative of the left-hand side, derivative of a is just 1 times dA dt. This is all implicit. Derivative of pi r squared. So pi is just a constant. Derivative of r squared will be 2r, and then because we're doing implicit, I apply the chain rule. I have to multiply by dr dt. All right, very good. Now let's see. They want dr dt, so let's isolate dr dt now. Dr dt is equal to dA dt divided by 2 pi r. My physics teacher would always make me isolate what we're solving for first before I plug in all the info that they gave. And then now I'm ready to roll. So dA dt they gave us, that's 7. I'll put that in the numerator. And then we have 2 pi, and then r is 152. This is when I use that specific info. They want it at the moment when the radius is 152. Now's my time to plug it in. Okay, I'm not gonna reduce it or anything. It just said we need to round our answer to 4 decimal places. So I'm gonna go ahead and do that. Just put it in the calculator. And you're gonna get 0.0073, and then check your units. This is rate of change of the radius with respect to time. So the radius is being measured in millimeters, and time is being measured in seconds. You have to get that right. But the units of the numerator should match the variable in the numerator, and then same thing. Denominator units match whatever time is being measured in. Okay, that was a cute little warm-up. Ready for another one? Here we go. So a piece of land is shaped like a right triangle. How convenient for us. 2 people start at the right angle of the triangle at the same time, and they walk at the same speed along different legs of the triangle. So basically 2 people start here and they're walking along the edges of the triangle and they're walking at the same speed. So here's one person, here's another person walking at the same speed. So whatever distance they're covering is the same, right? As they're walking, these are the same. Okay, if the area formed by the positions of the 2 people and their starting point, so the area formed by these 2 people, wherever they may be, it's going to change. Like at one moment, this is the area. Then at the next moment, that's the area. That area, the rate of change is 5 meters squared per second. Then how fast are the people moving when they are 4 meters from the right angle? Round your answer to 2 decimal places. Okay, 5 meters squared per second. What does that represent? That's rate of change of the area with respect to time. If you can't tell, look at the units. Meters squared. Squared quantities, that's always going to be 2-dimensional. That's going to be area. So you should be able to figure out that's dAdt. dAdt is 5 meters squared per second. What do they want from us? They want to know how fast are the people moving. So how fast they're moving, if I'm calling this distance that they've covered x, what they want is the rate of change of x with respect to time. How would you write that? Using a derivative, using calculus notation. That's dx dt, right? So that's what they want. They want dx dt. Specifically, they want dx dt when they're 4 meters from the right angle. So they want it when x is 4. We're going to save that for the end, okay? So now you're just going to focus here on the variables that they gave you, x and a. Can we relate the area of this triangle and x, the distance that they've each walked? Well, yeah, we know the formula for area of a triangle is 1/2 base times height. And in this case, since we have an equilateral triangle, both the base and height are x. So I can write area equals 1/2 base times height, or basically area is 1/2 x squared. Okay, great. So I've got an equation that relates my variables. That's why it's called related rates. And then now we need to differentiate both sides, always with respect to time. Don't even think about it. Don't question it. It won't change, okay? So you take d dt of both sides. Got to do implicit because none of the variables here are t, right? So left-hand side, derivative of a is going to be 1 times dA dt. Derivative of 1/2 x squared. So 1/2 times 2, those constants will just cancel each other out. I'll have x to the first times dx dt. Okay, and then let's see here. So we're trying to find dx dt. I'm going to isolate it now. So we know dx dt is equal to dA dt divided by x. They gave me dA dt, it's 5 meters squared per second. And x, now's the time where you can say, okay, I want this rate of change specifically when x is 4 meters. All right, lovely. How do they want our answer? Let me put units on it for shame. This would be meters per second since x is just a length, 1-dimensional, meters per second. They want the answer rounded to 2 decimal places. So I'm not going to leave it as 5/4. I don't have to round. 5/4 is exactly 1.25 meters per second. That's how quickly they're walking. That sounds very brisk. Trying to think, I think they are running. Okay. Anyways, now that the spice level is going to increase dramatically. All right, enough with these little warm-up problems. The volume of a sphere is increasing at a rate of 7 centimeters cubed per second. Find the rate of change of its surface area when volume is 4/3 pi centimeters cubed. Don't round your answer. Okay, so let's see what they gave us. They gave me the rate of change of the volume of a sphere. You can already tell that's a rate of change for volume because it's centimeters cubed. So that means dV dt is equal to 7 centimeters cubed per second. They want the rate of change of its surface area when the volume is 4/3 pi centimeters cubed. So what they want is ds dt, if S represents surface area, when the volume is 4/3 pi centimeters cubed. Okay, so do we have a formula that relates the volume and surface area of a sphere? No, we don't. I'm sorry. But we can create one, or we can use the fact that the volume of a sphere is related to its radius, so is the surface area of a sphere. So we're going to take a little detour and find the rate of change of the radius and then answer the question. Now, if you don't know the formulas for volume and surface area of a sphere, then I'm going to remind you right now, and you're just going to have to put these to memory because you will use them extensively throughout the rest of your calculus career. So if you haven't seen them, it's okay. Now's the time to just memorize them and put them somewhere safe in your brain, okay? Volume of a sphere is 4/3 pi r cubed. Surface area of a sphere is 4 pi r squared. I'm not really inclined to solve for r and make an equation that relates v and s, though you could do it. So what I'm going to do instead is, here's my plan of attack, okay? Strategy to solve. 1, find dr dt using the volume equation. And then 2, I'm going to find ds dt after, okay, by taking the derivative of the surface area equation. All right, very good. So let's go ahead now, figure out what dr dt is, because that's the third variable that comes into place secretly, okay? So volume is equal to 4/3 pi r cubed. I'm going to differentiate both sides with respect to time. So on the left-hand side, we're going to have dv dt equals. Just keep 4/3 pi, that's just a constant. Derivative of r cubed is going to be 3r squared times dr dt. Yes, are we okay? Oh, good. Okay, now from here, let's see, the 3's cancel out. And remember, I'm trying to just isolate dr dt. So dr dt is going to equal dv dt divided by 4 pi r squared. Okay, great. So they gave me dv dt, didn't they? They said dv dt was 7 over 4 pi times r squared. Well, what is r squared going to be equal to? Did they give me any info about the radius at the moment of time when they want that rate of change of the surface area? No. They told me they want the rate of change of the surface area when the volume is 4/3 pi centimeters cubed. Oh, that's okay. I can figure out the radius. If they told me the volume is 4/3 pi, that means this 4/3 pi is equal to 4/3 pi times the radius cubed. Well, then I can see that means 1 is equal to the radius cubed, so the radius must be 1 as well at this moment in time when they want the rate of change for the surface area. So I'm going to replace that with a 1 squared. Okay, so rate of change of the radius with respect to time is 7 over 4 pi. And they said don't round your answer, so I'm just going to leave everything in terms of pi. Okay, so step 1 is done. We found dr dt. Now we're going to find ds dt. So surface area is equal to 4 pi r squared. Now I'm going to differentiate both sides with respect to time. So derivative with respect to time, both sides, always with respect to time. Don't invent some weird new way to do related rates. It won't be right. Okay, left-hand side, we're going to have ds dt. 4 pi just stays. It's just a constant. Derivative of r squared is 2r dr dt. Okay. And now I can just go ahead, substitute in everything that we have. So 4 pi times 2 times r is 1, and dr dt is 7 over 4 pi. Oh, well, the 4 pi's cancel. How lovely. And all I'm left with is 2 times 7. So let's summarize our answer nicely. ds dt is equal to 14. What would the units be? So S is surface area, okay? So it's going to be units squared. In this case, it's centimeters squared per second. That's our final answer. You know, I didn't put units on the radius, dr dt. It's centimeters per second, but that was not our final answer. Okay, just always make sure the units are on your final answer. All right, this one was definitely tricky because along the way we had to find dr dt. I have had students that just relate V and S and bypass that, but their work is a little more messy. I think this is the cleanest way to do it, but you know, you do you. I've got one more, also a cute little spicy one. So the volume of a rectangular box with a square base remains constant at 500 centimeters cubed as the area of the base increases at a rate of 6 centimeters squared. Find the rate at which the height of the box is decreasing when each side of the base is 15 centimeters long, and don't round your answer. So here's what's going on. We've got a box, the base is square, and the iPad doesn't want to draw nicely today. There's something on the screen. Let's put the box over here. Maybe everyone will be happy now. Love it. Okay. The base is square. And then the third side, the height changes as the base is also changing. So I'm going to call each side of the base X, and I'll call the height Y. You can do you, but I think this is the best. It says the volume remains constant. So the volume is always 500 centimeters cubed as the area of the base, okay, increases at a rate of 6 centimeters squared per second. So the rate of change of the area of the base, I'll just call that dA dt, equals 6 centimeters squared per second. Find the rate at which the height is decreasing when each side of the base is 15 centimeters long. So what they want is basically dy dt when x is 15 centimeters, okay? And the height decreases as the base increases because the volume remains constant. So if the volume remains constant, I want you to think about something. What would dv dt be equal to? What's the derivative of a constant? It's 0. Okay, so the rate of change of the volume is 0. Okay, so how are we going to relate the variable y, since they want dy dt, with a? Well, area comes from the rate of change of the base, which is x squared. Okay, so let's go back there. And then we're going to have to kind of do something similar. So I'm going to find dx dt. And then once I have that, then I'm going to go back and find dy dt. Okay, so again, plan of attack, we're going to find dx dt using the fact that dA dt is 6 centimeters squared per second. And then step 2, I'll find dy dt by differentiating the volume. And the volume, let's think here, is length times width times height. So it would be x times y, or x squared y. We'll do that at the very end. Okay? So step 1, let's find dx dt using the fact that dA dt is 6. So how would you find the area of the base? It's just x squared, right? So a equals x squared. Now, differentiating both sides with respect to time, we have that dA dt is equal to 2x dx dt. So that tells me dx dt is equal to dA dt over 2x. We should have all that info. dA dt is 6 centimeters squared per second times 2, or divided by 2 times x. What is x? 15. So that goes right there. That's 6 divided by 30, which reduces to 1/5. And this is dx dt, so the units would be centimeters per second. Okay, great. Now I'm going to go ahead and find dy dt. Step 1 is done. I'm going to take the derivative of the volume. So volume equals x squared times y, differentiating both sides with respect to time. Let's see what we get. So on the left-hand side, we're going to have dv dt equals. To differentiate x squared times y, we have to use the product rule. Okay, so here's basically one function. You could think of this as f, and this is g. So derivative of x squared with respect to time would be 2x dx dt times y, leave y alone, plus, now leave x squared alone, derivative of y would be 1 times dy dt. Okay, great. All the calculus is done. Now we just have to solve for dy dt. And let's go through, make sure we have everything. X, we know, 15. dx dt, we just got it. Y, we don't have. Okay, we'll figure out what y should be. And x squared, 15 squared, so we're good. What about dv dt? Well, we said in the beginning of the problem, remember, since the volume was constant, that means that dv dt is equal to 0. Okay, and they did give me that x is 15. So if I know each of these sides is 15 and the volume stays 500 centimeters cubed, I can solve for y. Okay, so let's quickly off to the side find y when x is 15. We know the volume is equal to x squared times y. So y is the volume divided by x squared, which is 500 divided by 15 squared. That's 500 divided by 225, which reduces to 20 over 9. Okay, look at us. So then now let's start substituting in what we have. This is going to be 0, yes, equals 2. My physics teacher would be mad at me right now, but whatever, I'm just doing it. Times 15 for x. dx dt was 1/5. And y is 20 over 9 plus x squared, 15 squared times dy dt. Okay, so this is going to be 0 equals, what is this? This is 30 divided by 5 is 6. So we've got 6 times 20 over 9 plus 225 dy dt. Subtracting over, let's see, 6 times 20 over 9, that's going to reduce, right? This is 2, this is a 3. So now I've got negative 40 over 3 equals 225 dy dt. So dy dt equals negative 40 over 3 times 225. And then that will reduce to negative 8 over 135 centimeters per second. Okay, let's see if we answered the question properly though. So notice here, they said find the rate at which the height of the box is decreasing. Decreasing implies that the rate of change is negative, which we found, that's true. So when you answer the question though, you would say it's decreasing at a rate of 8 over 135 centimeters per second. Basically, the word decreasing is your minus sign. That implies that it's negative. If the problem had just said, find the rate of change at which the height is changing, right? Changing is neutral. It doesn't imply that it's going up or going down. Then you would put the negative sign. Okay, so pay attention carefully to directions, because it's wrong if you put the minus sign after the word decreasing. You need to answer the question the way they asked it, you know? It's like if you're given a job and you don't follow directions, no one's gonna like that. So same thing here. So that concludes the video. If you want more examples, let me know. And if you haven't subscribed to my YouTube channel already, please do so. I would appreciate your support so much. You can also join this channel to get access to exclusive content and uploads. I also upload pretty much daily, and you can catch me on TikTok and Instagram as well at Math TV with Professor V. Have a great one, you guys.